Let's get ready to review for the weather test. All right, the first thing we want to talk about is convection currents, and we're going to use the situation as the beach as a great example. Let's say we're at the beach during the daytime. So the sun is out, the sun is shining. The sun's rays are shining down on the beach and on the water. Okay, the first thing we need to know is that this type of energy transfer, there's three types of energy transfer. This first type of energy transfer is called radiation. And we're not talking about radioactive things that turn lizards into Godzilla. We're talking about rays, energy transfer in the form of rays. So energy transfer from the sun to the sand is through the process of radiation. As it comes down, it heats up both the sand and the water. Now the sand heats up faster than the water does. So that makes, by midday, the sand hot and the water is cool. So you have cool water and you have hot sand. Okay, since the sand is getting hot, what's going to happen to the air that is over the sand? Well, the air that is over the sand is going to start to heat up as well. Okay, so the air heats up. This air heats up because it is in contact with the sand. This is the second form of energy transfer, which is conduction. All right, the key word that goes with conduction is contact. And this happens because the particles are bumping into one another. The particles of sand are bumping into the air particles, transferring their energy. Okay, so once the air that is above the sand is heated up, it starts to rise because things that get hot expand, which makes their density lower, and they begin to rise. Well, this air can't rise forever. Eventually it cools down. And over the water, you have cooler air. The exact opposite is happening. So the air begins to drop. Over the water, we start to form a convection current, which is our third type of energy transfer. So third type of energy transfer is a convection current. You'll notice that the air is moving towards the beach. This is a breeze. We actually call this a sea breeze. Sea breeze because it is a breeze which is coming in from over the sea. Okay, this is what happens during the daytime at the beach. Now, if we go to what's happening at nighttime at the beach, the situation changes a little bit. At nighttime at the beach, the water is warmer. While the water heats up very slowly, it also cools down very slowly. Sand heats up very quickly, but it also cools down very quickly. So the water is warmer at night. If you've ever gone for a walk on the beach at night barefoot, you know that the water will feel warm while the sand is cold and wet. So this is cold. So the exact opposite situation is occurring here. At night, air is rising over the warm water. It is falling over the cold sand, and the convection current is the exact opposite. This is known as a land breeze. Okay. Again, this happens because of density. The key word when we talk about the third convection current, we had rays for radiation, contact for conduction. The key word here is density. Right? Warm air, because it expands, is less dense and rises. Cold air, because it's contracting, has a lower volume. Remember, density equals mass divided by volume. When we make this number smaller, it makes the overall number bigger, and the density increases, which makes things fall. When things have a higher density, they sink. When they have a lower density, they rise. All right, next we're going to talk about a cold front. And we have some more of the same concepts going on here. First, if you see a weather map and you see that they're often in blue, although they won't be on your test because your test is in black and white, but they have triangles on them. You can think of those as icicles. You can think of those as teeth giving you frostbite. And they point in the direction that the front is going. So when you look at a weather map, that's a top view. All right, so if we were to do a side view on our weather map, let's just draw a little box down here where our side view is occurring in. We'll do our side view in here. And we'll say that the ground is down here. All right, and the cold front comes through low to the ground. And cold air would come through low to the ground because it's more dense. Like we talked about over here, when things get cool, they begin to contract and they sink. And since cold air is more dense, it sinks. So as this cold front moves through this direction, it's going to take any air that is here and push it up. So we're going to see the air that is here getting pushed up. Right? That causes there to be low pressure here. When air is pushed up, there's low pressure. Now this air rises, and as it rises, it can no longer hold as much water as it used to, because this air was warm down here. As it gets pushed up further away from the land, that air starts to cool. Since the air can't hold as much water as it used to, that water has to go somewhere. So it starts to condense, which is a phase change, a physical change if you remember. It'll start to condense on dust particles, pollen, other stuff up here. And so you start to form these really menacing looking cumulonimbus clouds. Right? We see these are the kind that we get nervous when we see. And they get darker and darker as this wind is starting to pull up into the cloud. Eventually, there's so much moisture in there that the cloud can't sustain it anymore. And we start to see rain, intense rain happening at this low pressure cold front. So you get intense rain. There may even be enough static charge to allow for there to be thunderstorms. Now this air that's rising can't keep rising forever. Eventually it's going to cool down, get more dense, and want to sink. But it can't do that here because there's more air rising beneath it. So it moves to the side where we complete our convection current. Where the air is coming down, we get a high pressure. The air behind this is going to be cool, but not as stormy. The stormy is what happens at the front. All right, so when we talk about cold front, we're talking about stormy, intense weather. This is the kind of weather that can cause tornadoes to happen. All right, the opposite would be true if we were to talk about a warm front. A warm front has a symbol that looks like, I think of it as suns, because suns would be warming. Again, it moves in the direction that the symbols are in. So this warm front here is moving here. Air behind the warm front would be warmer. All right, let's take this is a top view if we were to look at a weather map. If we take a look at a side view, like we did before, if cold air comes through low to the ground because it's more dense, then warm air does the exact opposite. Warm air comes through very high. And warm air tends to move slower because it has to try to push all this other air out, but it has to do it from the top, where cold air can kind of plow through it. Cold fronts move through much quicker. Warm fronts move much slower because they're taking up all this from the top. Now, as this warm front moves in, during this area right in here, you have mixing of this warm, moist air with the cooler air down here. And this is the warmer air in the front. In this area, you start to get some mixing, and the air begins to cool. So this warm, moist air can no longer hold as much water as it used to. Again, like we said before, it needs to condense. But it's not going to condense as fast as it did. It's not being forced up rapidly into the cold air above it. So in here, you end up with these large clouds. But instead of the intense rain that we got before, we get more of a light drizzle. So warm fronts and cold fronts both bring rain, but a warm front is a drizzly rain, a prolonged rain. It's going to last a lot longer. A rain shadow is just like a regular shadow. With a regular shadow, we hold our hand up to the light hits our hand, and the area behind it, you don't get any light because it's blocked. Same thing, except here we're talking about with rain. So if we had air that was moving in from over the moist water, over the ocean, that air comes in and it came and there's a mountain in the way. Clearly that air can't move through the mountain, so that air has to move up. So that air moves up, it gets colder. Colder air can't hold as much water. So the water that it had has to go someplace. So we end up with rain on this side of the mountain. We call this the windward side of the mountain. Okay, and then that air keeps going, moves over the mountain. When it drops back to this side, it no longer has any of the water that it initially started with because it dropped it all on this side of the mountain. We call this the leeward side of the mountain. This side, the leeward side, is going to be dry. Often we find deserts on this side. On the windward side, it's extremely wet. Sometimes we'll even find rainforests and very moist areas over on this side of the mountain. Okay, if we look at the United States and we look at Olympia, Washington, and we look at Denver, Colorado, we can try to figure out which city would we anticipate to be colder. And if you just think about it in terms of how far north, the latitude, you might think that Olympia, Washington would be colder. It's much further north. But what you have to remember is that you have the ocean right next to Olympia, Washington. So the ocean next to Olympia, Washington, at its coldest may get down to 50 degrees Fahrenheit. That would be extremely cold ocean water if you ever were to jump in it. But Denver, Colorado has no ocean next to it. The air over this land may get down to 20 degrees Fahrenheit. So while Olympia, Washington has a 50-degree wind blowing over it the entire time, Denver, Colorado has a 20-degree wind blowing over it on the winter. So Denver will get to be much colder. We could think about the same thing with Columbia, South Carolina, and Santa Fe, New Mexico. If we thought about those during the summertime, you might think which one gets to be warmer and say, oh, well, they're both about the same latitude, they're both about the same northness, so I think they would get about the same temperature. But we know that Columbia, Washington is again on the water. Because Columbia, Washington is on the water, its temperature out here may get to 80 degrees. That'd be some very warm ocean water. Arizona and Nevada, we could easily see 115 degrees Fahrenheit out here. So the winds coming in on Santa Fe are well over 100, where the winds coming in to Columbia are much cooler, 80 degrees. So the effect that water has on the climate of the cities that are near it makes it more moderate. Cities that are close to the water have warmer winters, and they have much more mild summers, cooler summers. So cities that are landlocked, like Lincoln and Topeka, they have much more extreme temperatures. The weather gets hotter in the summer and colder in the winter. And finally, if we were to look at the tools that you would find used when we study weather, this tool right here is a sling psychrometer. Sling psychrometer. It is used for relative humidity. We should all be familiar with this tool right here. We've been using them in science for a long time. This is a thermometer. And a thermometer is used to measure temperature, how hot something is. Okay, this tool right here, these cups spin around, and the faster they spin records how fast the wind is. This is known as an anemometer, and it measures wind speed. And finally, these two tools right here are both barometers. They're different forms of barometers. Barometers are used to measure air pressure. Remember, the higher the air pressure, high air pressure tends to equal happy weather. When our air pressure is high, clear skies. Low air pressure equals lousy weather. So hurricanes and tornadoes, they occur at low pressure.